Okay, so now we are also recording. So I would like first of all to say I'm very sorry for the technical delay. So now everything is working. And so please, Nicole, the stage is yours. Thank you.
Great. Thanks for getting everything set up. So hopefully you all can see the start of my lecture notes here. We're going to start with a quick review of what we covered yesterday, then talk about the homework, then go back to Sealard's engine and look at other iterations of it and what we can do with it in the quantum realm, then talk about work and heat in quantum thermodynamics. So yesterday, we saw Sealard's engine, the synopsis of which is, if you have information, you can use it to turn useless heat into useful work. We covered a little bit of background about thermodynamics and quantum information theory. We said thermodynamics has some personality traits, for instance, it's operational. We reviewed the concept of equilibrium and the laws of thermodynamics. As far as quantum information theory goes, we talked about what it is and talked a lot about entropies. We focused on the Shannon entropy and the von Neumann entropy, and we saw that those can serve as optimal efficiencies with which we can perform operational tasks, such as data compression in information processing or the compression of a gas in thermodynamics. So we talked about how entropies unite quantum information theory and thermodynamics, as well as an operational viewpoint. Yesterday, we saw this problem that there is a ratchet, which is this wheel-like thing with teeth, and a spring mechanism, as well as a pawl that can fall on one of the teeth and prevent the ratchet from unwinding. So we said, suppose that this ratchet is in thermal equilibrium with a bath at a temperature T, such that the bath can kick the ratchets in the winding direction so that it can wind up the ratchet, perform some work, which is stored as spring potential energy. But it can't unwind the ratchets because the pawl will prevent the ratchet from unwinding. So it looks like this violates the second law of thermodynamics. So we had to figure out how do the ratchet and pawl not violate the second law of thermodynamics. But if you're on Zoom and you have a solution to the problem, can you please raise your hand? Then, Gabriel, would you like to pick someone who has raised a hand and unmute them and turn on their video so they could explain?
Sure thing. So let's just give a second for, okay, so I'll try to randomly pick someone. Okay, so Deborah, if you could.
Hello.
Hello, hello. Can you turn your video on as well? Okay, hi.
Good afternoon, Nicole. Good morning, Gabriel. I am Deborah. I am a professor in Federal University of Uberlândia, Minas Gerais. And the hatch and pawl problem is a problem that the gas share the fluctuations with the engine, with the hatch and pawl. Then the fluctuation could share the Brownian motion, and this Brownian motion do not violate the second law of thermodynamics.
Yeah, thanks for sharing your answer. And good to see a few of the faces in the course. Yeah, and in particular, our pawl here is also in thermal equilibrium with the bath. So the bath kicks the ratchet to wind it, but it's also going to kick the pawl. So the pawl will lift up and jiggle around and eventually let the ratchet unwind. So as you said, if the ratchet exhibits Brownian motion, so does the pawl. So it'll sometimes lift up and let the ratchet unwind. Give a little more background about this problem. It's called the Brownian ratchets for obvious reasons, as well as the Smoluchowski-Feynman ratchets. So this was written about, for example, in Richard Feynman's Lectures on Physics. In volume 1, chapter 46. That has a more detailed analysis than the one that we have here. So this is the Feynman lectures, I think, are available online for free, but I'll post this lecture, this chapter, on the course website for ease of everybody. So this problem is an example of a game that I like to call, Why Doesn't the Second Law Break? It's a fun game. You can play it with your friends over lunch. You propose what seems like a perpetual motion machine or something equivalent, and then everybody else figures out why it doesn't actually work. So you can have the most fun lunch table around. Are there any questions about the homework? Okay, Sawada, would you like to ask your question in the chats? And let's see, Gabriel, do you think it's best to unmute people who have their hands raised or ask them to write questions into the chat?
So my experience is that if the question is quick, maybe for the student asking in the chat is simpler, but some people in YouTube, they just ask that you read the chat question out loud so that they know what is being asked because they don't have access to the chat window from Zoom.
Okay. Can it be possible to set up a system so the ratchet cannot unwind? It seems like that would violate the second law of thermodynamics. And since the ratchet is small enough to be wound up by the heat bath, the pawl should also be, well, it's of comparable size, so it'll also be at thermal equilibrium. So it seems like that possibility of setting up a system so the ratchet doesn't unwind would violate the second law, which we're guessing can't happen. If the pawl were isolated from the gear, then it seems like it might not do such a good job of its original job, as in preventing the ratchet from unwinding. But if you can manage to design such a system, you can probably make a lot of money and publish a lot of papers. What happens if some daemon closely observes the setup and uses the spring to generate work as soon as the ratchet is wound up? I guess that in that setting, there would also be some matter of the systems just being so small that everything is going to be, or some things are going to be in thermal equilibrium with the bath, and those things are going to jiggle around, so they're going to let go of work. And if you have anything that isn't at thermal equilibrium with the bath, then it's a resource. So it could actually be the source of the work that you're doing. Okay, let's move on to further analyses of the Szilard engine. First, we had our homework problem, which is also a small engine, so it's at least related. We said that the synopsis of Szilard's engine is information plus heat yields work. And in part 3, we will reverse the engine. This story was developed by Rolf Landauer, who worked at IBM. in 1961. Here's our setup. We have, once again, a classical particle in a box. This is going to model a very idealized ideal gas. Now we have no idea where the particle is. Again, the bath interacts with a temperature T, the gas interacts with a temperature T heat bath through the walls of the box. So heat can go in and out. And we have a reservoir of energy that can serve as work, such as a raised Acme anvil, which stores gravitational potential energy. Our goal is to reset the particle's position to a well-known state, namely to the right-hand side of the box. This is analogous to taking a messy sheet of scrap paper that has scribbling all over it and erasing it to a clean, well-known fiducial state so that it could be the input to a new computation. So we can use this protocol. If I can write, there we go. So we slide a partition into the box near the left-hand side, and then we push the partition into the middle of the box by drawing on our work reservoir, which in the case of gravitational potential energy will be lowered. We can now analyze this protocol. We are compressing a gas, so we have to perform work. We can do basically the same analysis as we did yesterday and find that the work is at least Boltzmann's constant times the temperature times log 2. Why is there a greater than or equal to sign? Because we can always be silly if we want to and waste work on things like friction. So a generalization of this statement from the gas in a box is Landauer's principle. So erasing a bit of information. Costs work. This process of resetting the bits is called Landauer erasure. So in this case, we have traded work for information, which is sort of the reverse of what we did yesterday. But this protocol has some deep implications for computation and the relationship between computation and thermodynamics. So suppose that we want to compute and compute and compute. Eventually, we will run out of scrap paper, which we need for computations. We're going to have to erase scrap paper. And we just saw that erasure costs work. So computation, at least extended computation, has a fundamental thermodynamic cost. So information processing and thermodynamics are very fundamentally linked, which I just thought was the coolest thing when I learned about it, because if you approach the two subjects individually, well, at least when I approached the two subjects individually, I would not have guessed at all that they were very, very fundamentally linked in this way, but they are. Let's take a minute-long break and visualize, picture in our minds what we just heard and saw, and rest our eyes a little bit. Okay, any questions about Landau erasure? Why do we call it Landauer's principle? Because we can derive it in thermodynamics of memory. I once had a long conversation with someone about what exactly principle means and how it is distinguished from the various other types of statements we make in science. It's an argument, granted, some people argue with it. You could read Landauer's paper yourself and judge what you think the logical status is. We're going to see some quantum variations on this in a little bit. Is it related to the Loch-Schmidt echo? The Loch-Schmidt echo also involves a returning of a system to not necessarily its initial state. Well, in the perfect case, the Loch-Schmidt echo returns a system to its initial state. And in that case, that is, it involves a certain type of memory or returning to initial states. Loch-Schmidt echo can result from just a completely Hamiltonian process that doesn't involve dissipation, and is sort of dependent on the initial condition, whereas Landauer erasure is a protocol that works regardless of what initial state the system is in. So there are definitely some similarities. There are also a few differences. Right. Then there is another implication of Landauer erasure worth covering. This helps provide what is at least pretty widely regarded as a solution to Maxwell's Demon paradox. James Clerk Maxwell, the same Maxwell of Maxwell's equations, contributed quite a lot to thermodynamics. So he wrote this in 1867, I believe, in a letter. He didn't use the word demon, his colleagues did. Here's the story. We have, once again, a gas in a box. This gas has many particles. It's internally at thermal equilibrium. There's a partition in the middle of the box, and there's a trapdoor in the middle of the partition. So particles can go through in principle. So this trapdoor is operated by a demon, what Maxwell actually called a finite being. But we can replace it by a mechanical device. So if a particle approaches the trapdoor from the right, then the demon lets the particle through if and only if the particle moves at a speed above some cutoff. So fast particles can go through in that direction. And if a particle approaches from the left, then the demon lets the particle through if and only if the speed lies below some cutoff. Eventually, all the fast particles are in the left-hand side. And all the slow particles are in the right-hand side. Speed is related to temperature because temperature characterizes kinetic energy. So there will be a hot gas in the left-hand side and a cold gas in the right-hand side. So the daemon has created a temperature gradient. You can use a temperature gradient to extract work via a heat engine. And the daemon can be replaced with some machine that, unlike living beings, doesn't radiate heat. So the daemon seems not to increase its environment's entropy as organisms would. So the daemon seems able to extract work from an equilibrium system without increasing the system's total energy. So the daemon seems to violate the second law of thermodynamics. So we can figure out a way of resolving the paradox using what we just saw. And this resolution has been debated, but it's at least fairly widely accepted. Some of the key players in the resolution were Szilard, Landauer, and Charlie Bennett, who also works at IBM as Landauer did. The daemon is measuring particle speeds. So it acquires information. It fills its memory. The daemon would violate the second law if it could extract work without changing its own state. The change in the daemon could compensate for the work extracted, so the daemon could act as an entropy sink. But the daemon has changed because its memory is filled. And so the daemon could undo the change by erasing its memory. So if the daemon can erase its memory without paying more work than it extracted, then it can violate the second law. But according to Landauer's principle, the erasure does cost work. And in fact, the work cost of erasure will end up being at least as great as the work extracted. So the daemon doesn't actually violate the second law. Are there questions about Maxwell's daemon?
So Nicole, there was a question on YouTube. It was actually from the previous question break. Apologies, that was my fault. So the question is, why is it called the erasure if you gain information about the gas?
Yeah, there are multiple ways of looking at the situation. And that is something that I got hung up on originally as well. So the thing about one way to look at the situation, and again, there are multiple seemingly conflicting ways, is if you erase a system, if you erase a bit of information, then you have a physical system that's in some sense sort of clean. So you can fill it up with information. If you have a bit that starts out in the 0 state, then you can input it into a computer to perform computations. So in that sense, it's clean. So it's been erased off. Any computation, suppose that you are doing multiple computations on one set of bits. Then if you get to the end of a computation and you clean the bits off, you erase them, you get rid of whatever the computation, whatever state the computation put them into, that's like erasing, and that's like erasing a chalkboard so that you can now use it in a new computation. But I agree that that way of thinking can be counterintuitive.
Okay, cool. Thank you.
There seems to be a very active conversation on the chat. So erasing a bit costs work or heat. Erasing a bit costs work. We have to pay work. The work is dissipated. So it turns into heat. Not sure, you know, there seems to be a pretty active conversation and people are answering each other's questions. And some questions going back a little bit. For the sake of, since there are quite a lot of people and so a lot of questions, for the sake of going forward, at the moment I'll focus on just questions about Maxwell's demon. And I'm not quite sure what some of the questions mean. But if there are other questions, then you can write them in the chat. Maybe other people can respond to them, or if we have time at the end, maybe we can go through in more detail and talk about exactly what's being asked.
So if I may intervene a little bit, I think it would be helpful. I mean, try not to move a little bit off topic in the chat, okay, everyone? I mean, it's okay if one answers the questions of someone else, but let's try not to move too much off topic.
Yeah, this is a new experience to all of us, having a class of about 400 people. So we're figuring it out as we go along. So I hope that's okay with everybody. And thanks for your understanding. Let's think a little bit about if I can write. There we go. The significance of what we've saw in this Szilard engine section as a whole. We've now talked about Maxwell's demon, Landauer's principle, and Szillard's engine. These all form tropes, so forms or formulations that come back again and again across information theoretic thermodynamics. They're useful to know about because often we can take some problem and recast it as a demon or a Szilard engine, and then apply what we know about these canonical problems. How about quantum effects in Szillard's engine? Until now, we've been talking about just classical gases and boxes. First of all, many effects are known. I'll present just a select few, but if you're interested in learning more about the topic of a quantum Maxwell demon or a Szilard engine, I can point to a review in a book. This is the review. It's from 2009. And also there have been 2 books by Rex and Leff called Maxwell's Demon and Maxwell's demon 2. So there are a number of ways in which a quantum Sailor engine can differ qualitatively from a classical one. First, in the quantum scenario, inserting the piston.
Nicole, I'm sorry to interrupt. So someone is complaining. Somehow the iPad screen was shifted a little bit for some reason. So we're now seeing like it's cut a little bit to the sideways, to the side.
Now, can you see the whole thing?
Ah, yeah. Okay, now it's back. Perfect. Thank you.
Okay, thanks for letting me know. Inserting the piston can cost work. So this story comes from a paper from 2005. If we have a classical particle, it's fairly localized. And if the partition is somewhat thin, then there's going to be a very low probability that the classical particle would be right under the partition when the partition descends. But a quantum particle is in a quantum state that can be represented as a wave function relative to the position eigenbasis. And that's spread out in space. So suppose that the particle is in one dimension and has a mass m. Then we have our favorite quantum particle in a box problem. Suppose this is the x-axis. Here's the origin. Here's the box's length. We have this potential. And on the y-axis, we're going to draw the amplitude of the wave function. We can recall some basic facts from undergraduate quantum mechanics. The nth energy eigenfunction has a sinusoidal shape. Let's label it psi n of x. We have our normalization factor, then our sine. For n equal to 1, 2, and so on. The nth eigenenergy has this form. And so a general position space wave function has the form of a linear combination that evolves in time. I didn't mean to do that. So the C sub n's are our coefficients that make the state normalized to 1. We have our amplitudes, including a time-dependent factor. Suppose that the particle begins in an energy eigenstate associated with an even value of n. For example, n equals 2. So let me take away my absolute value sign here. We are going to insert the partition at a node. The particle has a probability of 0 of being there, because this, again, is a node. So the insertion costs no work. Now, suppose that the particle begins in an energy eigenstate associated with an odd n. Now we want to insert the partition somewhere where there is not a node. The probability of the particles being there, supposing that we measure the particle's position, is not 0 before insertion, but does vanish afterward. So the insertion changes the particle states. And since the particle begins in an energy eigenstate, changes the particle's energy. Does anybody have any questions about that? Okay, there is a question about Maxwell's demon again. Just for the sake of keeping the lecture going forward, let's focus for the moment on questions about the quantum Stillard engine. And maybe if we have time at the end, we can go back to earlier questions. Okay. Another qualitative difference between classical and quantum Stillard engines comes from particle statistics. It looks like there is a new question. So the insertion makes the state symmetric with respect to L/2. At least what we can say is that the state comes to have a node at L/2, so that the wave function comes to have a value of 0 there. You could have started with some crazy combination of many, many energy eigenstates, so that maybe it started asymmetric about 0, and then maybe the final state would still be asymmetric about 0. But at least we know that the wave function has a value of 0 there. So this sustained the idea for establishing the changing on eigenenergies as work. So that touches on a very deep question that we'll get to later in the lecture. How do we define work? In this case, there's no heat bath around, and we're performing a controlled operation by dropping the partition. So that's why we might be inclined to call that change in energy due to that work. But we'll talk about more types of ways of defining work later. Okay, this story comes from a paper from 2011, published in Physical Review Letters. We should establish a few assumptions first. First, for simplicity and concreteness, let's suppose that the engine contains exactly 2 particles. we can extract work from the engine only if both particles begin on the same side of the barrier. Because if the particles are split half and half on opposite sides of the barrier, then the barrier will experience no net force in either direction, so the gas won't expand. Second, we'll assume that the particles don't interact. This assumption was lifted in a number of later papers by other authors. Then we'll suppose that, at least in the case of quantum particles, the temperature is very close to zero, so that the system is approximately in its ground state. Finally, if the particles are quantum, then they obey spin statistics, but lack spins, which seems like a funny statement. We know that bosons have totally symmetric states, fermions have totally antisymmetric states, which leads to the Pauli exclusion principle. And there is a relationship between spins and fermions or bosons. So this might be something of a strange sounding assumption. It's, let's say, not my favorite one to make for practical purposes, but in some cases, you can think of a bunch of spinless fermions. For instance, a bunch of qubits can be equivalent to a bunch of spinless fermions via a mathematical transformation called a Jordan-Wigner transformation. But I think that the authors of this paper were less interested in implementations than in implications. So let's just suppose that this is the case. We can consider three cases within the engine's operation. First, suppose that the particles are distinguishable and classical. Then there are four possibilities for how the particles can arrange themselves, or four possible outcomes of our position measurements. Particles A and B could be on the left-hand side of the barrier, or particle A could be on the left-hand side while particle B is on the right-hand side. Particle B could be on the left-hand side while particle A is on the left-hand side, or both particles could be on the right-hand side. All these possibilities are equally likely. So in 2 out of 4 cases, or half the cases, the particles are distributed unevenly. So we can extract work from the engine. In case number 2, the particles are bosons, which implies that the particles are indistinguishable. So we can't label them A and B. Now, there are 3 possibilities for how we could find particles arranged, or more accurately, 3 possible outcomes of our position measurement. Either both the particles are on the left-hand side, or one particle is on the left-hand side while one particle is on the right-hand side, or both particles are on the right-hand side. Again, all the possibilities are equally likely. In 2/3 of the cases, the particles are distributed unevenly, so the engine can perform work. Finally, suppose that the particles are fermions, but don't have spin states. So the only degree of freedom that we'll attribute to them is position. Now there's only one possible outcome of our position measurement. Both the particles have to be on opposite sides of the barrier so that they don't violate Pauli's exclusion principle. The particles are always distributed evenly. So they can never perform work. In conclusion, suppose that you run a whole bunch of trials, measure the work in each trial, and then average over trials. On average, over trials, the work you can perform using bosons exceeds the work you can perform using distinguishable particles, classical particles, which exceeds the work performable by fermions. Furthermore, we're not going to show this here, but as the temperature rises toward infinity, all the quantum particles become distinguishable, and all average work quantities approach the distinguishable value. Let's take another minute-long break and review what we just saw in our mind's eyes. Does anybody have questions about particle statistics in Szilard's engine? Why do they tend toward the distinguishable? Why do the values of the work tend toward the distinguishable work value in the limit as t approaches infinity? In the limit as t approaches infinity, we leave the quantum regime. There are a number of, we have a system that has a number of parameters, like the number of particles, the temperature, and if you change some parameters past some point so that you cease to satisfy a certain position, a certain condition, then the particles cease to be in the quantum regime. But why only an even distribution will cause work? If the particles are distributed evenly across the barrier, then neither side will exert more pressure on the barrier than either other side, than the other side. And it's the unevenness in the pressures that enables one gas to expand, to push the piston against the other gas. For the distinguishability as t approaches infinity, this is a topic that's often covered in statistical mechanics classes about conditions under which systems act quantumly in a quantum manner or can be governed by classical statistical mechanics. You come up with two lengths. One characterizes the quantum the wavelength of the quantum system, and the other is a comparable thermal length, as it's called. And so you compare these two. And in one regime, the system is dominated by by quantum behaviors. In the other regime, it can be described as quantum. In the case of fermions with spin, the work is the same as W distinguishable. I think so, because you can, the spin degree of freedom can distinguish the particles, though I would have to write all of the cases out to check. fun thing to do for homework. Suppose that the fermions do have spins, then figure out what cases are allowed and calculate the average work. Are the calculations done with the particles in a thermal bath? If so, when considering the master equation, was the global or local approach used? You could check the paper by Kim et al. They have some calculations and show a plot. Did you make the spinless fermion assumption for convenience? So I was following the paper because that's what they do. And I think they say that they do it for simplicity. I think it's really to make the point that if you can consider spinless fermions, which again, we can construct in certain cases, then there's this very easily observable difference between bosons, distinguishable particles, and fermions. So I think that assumption was made in that paper to make a point. Are there examples of engines that use cold atom gases? There have been a lot of realizations of quantum thermal machines. We'll talk about some quantum thermal machines in a later lecture. And by now, I think the number of platforms used to implement quantum thermal machines is, well, it's at least growing. So there's a lot of literature. I can't say no every paper in the literature. What about anyons? That's an interesting question. Seems like a good opportunity for independent research. Okay, let's move on to a third way of distinguishing quantum from classical Szilard engines. If the system is quantum, then the agent can have a memory that's entangled with a particle in the box. So actually, the story is a variant on Landauer erasure, not directly Szilard's engine, but it's basically the same thing to within some reversing. This story comes from a paper by Lidia Del Rio and friends. That was published in 2011. The setup will be a little bit different. Now we have a system of interest S, which is the particle in the box. There's a system O that's a memory correlated with S. This memory might be entangled with things other than S if it's a large memory. So we introduce a reference system R. That is everything else that O can have information about. Let's denote by rho the reduced state of SO at the beginning of the protocol. We need to calculate the minimum work cost, which we'll denote by W of S given O, of erasing S given O, while preserving the reduced state of O, which I'll denote by rho sub O. We want to preserve rho sub O because the system O, again, might be entangled with R, and we don't want for the erasure to disturb R. The result, I won't go through the derivation since we don't have time, but you can find it in that paper. The result has an illuminating form. The work cost is the conditional entropy, which I'll define in a moment, of S given O, times the familiar factor kBt log 2. In this section, when I write an H, I'm referring to the von Neumann type of that entropy. What is this conditional entropy? We said that we would meet more entropies than Shannon's and von Neumann's entropies during the last lecture. This is one of the alternatives. So it's defined as the entropy of the joint state rho minus the entropy of the reduced state of O. And this signifies our uncertainty about S, given that we know O. This is explained in Nielsen and Chuang's quantum computation textbook in terms of a Venn diagram that I like. So suppose that this loosely represents all the information possible about S. This represents all the information possible about O. Here's our joint system, or the information about our joint system. Then suppose that initially we don't know anything about any of these systems. So our uncertainty fills up both circles. Now, suppose that, so that is our representation of this joint entropy. Now, suppose that, in fact, we obtain information about O. We can delete the scribbling in the O circle and leave just the scribbling that's over part of the S circle. That's the representation of this difference. One cool thing about this result is if S is entangled with O, then the work cost can be negative. Namely, you can extract net positive work. For example, suppose that S and O are qubits. And suppose that S is maximally entangled with O. Then the joint state of the two systems, rho, is pure. So as we said yesterday, its entropy is 0. On the other hand, since O is maximally entangled with S, the reduced state of O is maximally mixed. And so as we saw yesterday, this entropy is log 2. I'm now using base E because we're doing thermodynamics. And so counting entropies in nats, namely the unit of information when you use base E in an entropy, is useful, as we'll see in a future homework problem. Therefore, the work cost, which is the first joint entropy minus the second entropy, times our favorite multiplicative factor. Wait, actually, I didn't mean to put that there. Yes, that should go away. Is negative. The work cost is negative, so the work extracted is positive. That seems counterintuitive because Landauer showed us that the erasure costs work. The trick in this case is we in a loose sense, sort of burn the correlations, the entanglement between S and O. So we can sort of think of entanglements as a thermodynamic fuel. After this process, S is in a maximally mixed state, excuse me, O is in a maximally mixed state. We've erased S, so they have no information about each other. Because we can achieve this result using the following protocol. We can extract work from the joint system SO. Since SO is maximally entangled, there is a measurement we can perform on SO such that there are 4 possible outcomes, and we can exactly predict which outcome we'll obtain. So we get one of 4 possible outcomes. We have 2 bits of information about the outcome. Using those 2 bits of information, we can create 2 runs of our Szilard engine, or fuel 2 runs of our Szilard engine. Then, in accordance with Landauer's principle, we use half that work to erase S. Okay, are there any quick questions about entanglements in erasure?
So there is a question from YouTube, which is a little bit before that, from Fernando Mileto, which is it possible to know all the memory of the entropy?
I'm afraid I don't quite know what that means.
I think he's referring to the entropy of the auxiliary. To know all the entropy of the auxiliary device, the O part of the system.
And we suppose that the agent has O, holds O, has access to O.
Okay.
Okay, and let's move to talking about work and heat in quantum thermodynamics. First of all, why is this topic even worth a section in our mini course? So consider the following scenario. We have a quantum gas in a box. It's exchanging energy with a fixed temperature bath, and we compress the gas. So we expect the bath to exchange heat with the gas, and we expect the compression to perform work on the gas. We have our gas here. We have a piston. We have an exchange of heat with the bath. This piston is compressing the the gas. So we expect this to perform work. How much heat and how much work? We need to be able to define these quantities and measure these quantities. At each instant t, the gas is in some state rho of t. It is not necessarily an energy eigenstate. So it doesn't necessarily even have a well-defined energy. We could calculate or measure the expectation value of the Hamiltonian at any given time. But that gives us an average over many trials. And we might want to know the work and heat exchanged in one particular trial. besides measuring the energy, disturbs the energy. So in quantum thermodynamics, defining and measuring quantum work in heats is non-trivial. Gabriel, did you say something?
No, sorry. Some people in the chat they were saying that the screen was not updating. Sometimes the refresh rate oscillates a little bit, but I think now it's better. It's back to normal.
Okay, good. I'm afraid I don't know how to control that, but I'm glad to hear that it's working. So if it gets very bad in the future, then maybe we could try to change some settings somewhere.
Yeah, I think this is only controlled by the deities.
Okay. So lots of definitions have been proposed. Different people have different opinions about the definitions. Different people have their own favorite definitions. My personal opinion is different definitions are useful in different contexts. Well, let's see, there are some questions. Okay, so people are talking about the delay. So here are some example definitions that have been or are useful in a number of contexts, some of which we will see. First, you could separate the heat exchanges from the work exchanges in time and measure the energy between the exchanges. In this protocol, we have a system of interest. Let's call it S. We have a heat bath R, and we have some work reservoir, some battery, in which we can store the capacity to do work. This could be, again, a battery that is filled up to some level. Then we alternate between coupling the system to the heat bath and coupling the system to the battery. So we might enact this coupling from time T1 to time T2. Then we measure the Hamiltonian of the system of interest.
So Nicole, sorry to interrupt again. I think now it's got a little bit worse. So for some reason it's, I mean, we're seeing what you're writing, but it comes in chunks. Maybe we could try just, unsharing the screen and sharing again or something silly like that. Maybe that should help. It shouldn't take us too long. Okay, so can you give it a test drive?
If my pencil will let me write yes. It seems not to want for me to write now. There we go.
Okay, I think it's perfect now. Cool.
Okay, great. Then during the next time step, we couple the system to the work reservoir. I should have said, we measure the Hamiltonian of the system of interest at T1, T2, and T3. So we will get an energy at each of those times t. We define work and heat as follows. All energy exchanged with the bath is heat. So Q will be defined as the energy at time T2 minus the energy at time T1. And we define it as work, all the energy exchanged with the battery. The energy at T3 minus the energy at T2. This definition has some advantages. First, it is defined for single shots, single trials. And second, it's physically implementable. On the other hand, this protocol is somewhat artificial. Usually we'll have a system that's interacting with a bath and having its Hamiltonian changed at the same time. There is a partial counter to this criticism. Under certain conditions, if you let the difference between those special times go to 0, then the system evolves according to a master equation. Well, a master equation is a pretty natural description in continuous time for a system that's interacting with the bath, potentially while evolving under a Hamiltonian that's changing. So I think that Matteo might talk more about master equations. So that result is in here. Yep, I agree. The setup is fairly artificial, but it can be implemented in some cases, especially since we have good control over quantum systems nowadays, relatively good control. But yeah, I agree, it's artificial. Each of these definitions, I think, has its pros and cons. Are those measurements projective? Yes. We will see non-projective measurements and a different definition later. What is the physical system between the battery and the bath? We'll talk a little more about batteries later, so maybe that will make things clearer. The bath is usually some enormous set of degrees of freedom over which we have no control. Also, as was alluded to in the chats, a disadvantage is that measurements disturb the system's energy. However, in some cases, this definition can be useful. It's simple. It can be applicable to, for example, certain fluctuation relations, which form a toolkit of quantum thermodynamics that we'll talk about later. We could also define work in terms of control parameters. And heat in terms of the quantum state. Let's say that the average internal energy of our system denoted by U of t, is a trace of the state times the Hamiltonian at the same time. We can differentiate each side using the chain rule. The derivative of the internal energy equals the sum of two terms. First, we differentiate the states. Then we differentiate the Hamiltonian. The work is controlled energy. You perform work when you lift a weight in a gravitational field, or you strengthen a magnetic field, but when you tune a parameter that controls the Hamiltonian. So we can define this term as the work absorption rate. Consider a classical system exchanging heat with a heat bath. So the system will tend toward thermal equilibrium. Its probability distribution over phase space will flow toward the canonical distribution. So heat changes probabilities, and heat tends to mess up our ability to predict because it's random. So the density operator is the quantum generalization of the probability distribution. So we can define the second term as the heat absorption rate. These definitions have arguably the advantage of being somewhat intuitive. On the other hand, they contradict the definitions in condensed matter of heat. So consider a quantum system with some energy levels. Suppose that you periodically whack the system. In other words, you abruptly change its Hamiltonian. So this whacking is given the dignified name in condensed matter of Floquet driving. In most cases, the state will come to have equal populations on all of the levels. This is the same distribution that would result if, instead, the system were equilibrated with a T equals infinity, an infinite temperature bath. So condensed matter physicists call this whacking, heating, even though it's only the Hamiltonian that's providing energy. There are two more definitions that I'd like to get through. So we'll finish a little bit after 1/2 the hour in whatever time zone you are in.
That's no problem at all.
Okay, yeah, sorry, again, there was a bit of a delay at the beginning, so we should end hopefully almost on time. We can define work in terms of a battery. This is at least a definition for work, not necessarily directly a definition for heat. Here's the formalism. We have a system of interest. It starts in some state rho, and it's governed by some Hamiltonian H. There's also a battery in which we can store the capacity to perform work. In the simplest example, the battery is a qubit governed by some qubit Hamiltonian with energies E0 and E1. Also, often people will assume that the battery is always in an energy eigenstate. work extraction has the following form. The battery begins in its ground state. We perform some unitary U on the joint state. U is often assumed to conserve the total Hamiltonian. So it shifts energy from the system into the battery. So the system of interest will end in some state sigma, and the battery will be in its excited state. It's as though the battery were some object in a gravitational field that started off far down and ended up high up. Then work expenditure has the following form. Now the battery begins in its excited states. We perform some unitary U prime. We transfer energy from the battery to the system. The system ends in some state sigma prime, and the battery is lowered. This scheme has the benefits of being physical. We are describing work, defining work in terms of some physical battery system, and it is generalizable, at least to some extent. You might not know exactly how much work you'll need to spend, so you can devise a battery Hamiltonian that has many closely spaced levels. So the battery can end a little bit below or a little bit above where you expected. On the other hand, it's not necessarily realistic to assume that the battery is always in an energy eigenstate. After all, it too is a quantum system. It can be in a superposition of energy eigenstates, it can entangle. This topic was discussed in a 2014 paper. This strategy is often applied in resource theories. A toolkit within quantum thermodynamics, well, at least thermodynamic resource theories form a toolkit within quantum thermodynamics that we'll talk about later. The final definition that we'll discuss was alluded to in the chat earlier. We can measure the energy weakly. What is a weak measurement? It's not a standard concept taught in undergraduate statistical mechanics classes, or even quantum mechanics classes, or even standard graduate quantum mechanics classes. What's a weak measurement? Well, what is a quantum measurement? We have some system of interest, we have some detector, and we correlate the two. Then we measure the detector projectively. We receive some classical information from the detector measurement. From the outcome and the correlation, we infer about the system of interest. Usually we assume that the coupling creates maximal entanglement. Therefore, when we project the detector, we project the system of interest. And when we measure the detector, we can infer everything possible from one measurement about the system of interest. But the coupling needn't create maximal entanglement. We can couple the systems for short times, And we can use an interaction Hamiltonian that is much smaller in some matrix norm than the subsystems Hamiltonians. When we measure the detector later, then we can't learn much about the system of interest. And you might ask, why would we want to give up information about the system of interest? Because this scheme doesn't disturb the system very much. And not disturbing a system can be valuable in quantum settings. For example, a weak measurement needn't change the energy much. And if we perform many trials and process the outcome statistics, then we can infer what we could have inferred from strong measurements. This strategy has the advantage of disturbing the energy little. A disadvantage is that we tend to need many trials and can't say a whole lot usually about a single shot. This strategy has applications to fluctuation relations. I've used this in the context of fluctuation relations and contextuality, which is a certain feature of quantum theory that Matteo will tell us about. So now we've seen 4 definitions of quantum work and heat. They're useful in different times and in different ways. So I hope this exercise has demonstrated how quantum thermodynamics is not always a straightforward extension of classical thermodynamics. Now, we have time for a few questions. So let's see what we can get through in a few minutes.
Just a reminder that there are a couple of people with their hands raised. I know some people are asking questions in the chat, but there's also people that probably want to ask longer questions in the chat, I guess.
Okay, thanks. See, one question at the bottom is, can we not perform a quantum non-demolition measurement? We can perform measurements that don't completely destroy the system. Weak measurements are an example. Well, in certain cases, weak measurements are an example of that. Let's see. Gabriel, would you like to unmute someone who has a hand raised?
Yeah, of course. So let's see here in order. So Fernando.
Hi.
Hi, Fernando.
Hi. My question is for the end. It's about the Maxwell's demon. So I think that's better to talk about it at the end of the talk. What do you think?
Okay.
Okay.
Thank you.
Thanks for letting us know.
So the next one will be Soham. Let me see if I can unmute you. Yep.
Hi, am I audible?
Hi, we can hear you.
Yeah. So my question was regarding the second last definition of work in terms of battery. So what do you exactly, I couldn't follow you exactly. So what are you saying here, that you couple the system to a battery and then evolve it and then see what change happened in the battery, how much energy change happened in the battery, and then infer what the work is? Is that what you're telling?
Exactly. So the work, yeah, I could write that out more explicitly. In both these cases,
isn't that going around the thing? Because now how do you know whether that's work or that's heat? I'm a little confused.
So let me see if I can write this. For some reason, there we go. In these cases, yes, we define the work either extracted from the system of interest or performed on the system of interest as the change in the battery's energy. There's no heat bath around. The battery is a well-controlled system. We're assuming it's always in an energy eigenstate. It's the only thing interacting with a system of interest. And it makes sense to think of the energy as stored in a battery, the energy that's stored in a battery as work if it's easily extractable, because work is useful energy that we can readily access. So that's the idea behind this definition.
Okay, so here's the problem. So suppose you have two qubits and they are coupled to each other with some Hamiltonian which doesn't commute with the state, initial state. And you suppose have, and both both the qubits are in their diagonals, but the distribution is different. So I can assign different spin temperatures. Is that clear?
Assign different what?
Spin temperatures, as in both
Okay.
the qubits are in diagonal state, but they have different population distribution.
Mhm.
So now, if you couple them with a Hamiltonian which does not commute with their with their initial state, there will be a flow of energy from one qubit to the other.
Mhm.
But this will not be work. This will, in a sense, be energy transferring from one to other. But I wouldn't say this is work, right? Because in terms of the definition of the previous one, in which you said that the heat is something that which causes the change in the state, and here the Hamiltonian is not changing, or the Hamiltonian of the interaction is not changing. It's just that the state of the system is changing. So
That's one of the reasons why we have a whole section on this, and that there's no one clear winner every time as a definition for work and heat. So the previous definition, this tends to be useful when the process is very slow. And if you have, so if you have a setup in which the Hamiltonian is changing and the state is changing because it's interacting with something that could be providing it with heat and something that could be providing it with work, we just can't tell how much energy is going into or out of the system as a result of each source. So that's one setup in which people often use this definition shown here. Then this definition comes about when this is a way that people define work. As I mentioned, it's not used as a direct definition for heat, but just work. And here the idea is we have a different setup. And here we have a system of interest and some other system that's well controlled. So as you said, we can institute whatever coupling we want, or an extension of what you said is we can institute whatever coupling we want. And we regard this system, the second system, as a battery because we can reliably put energy into it and reliably extract energy from it. And those are characteristics that we tend to associate with work. So I agree with you that if you look at one scenario, then one definition seems better. If you look at another scenario, a different definition seems better. That's why there are a whole bunch of definitions. And yes, if you have a qubit that is in a state that's represented by a matrix that's diagonal with respect to the energy eigenbasis, then you can always artificially define a temperature for it. The qubits, if it's a qubit, it's not a heat bath. There are some models of heating of systems that involve qubits that interact with the system one by one. Usually there's a whole stream of those qubits to simulate an interaction with a heat bath, which tends to be something very big with lots and lots of degrees of freedom and a certain sort of spectrum. So if we have just one qubit, then we can definitely set one probability, one population equal to a Boltzmann factor, the other probability equal to another Boltzmann factor, and solve for an effective temperature. We usually don't think of that as the same temperature as a heat bath, which has sort of a physical temperature. It's definitely an effective temperature. And sometimes it's very useful to think of this as being like a temperature. We'll actually do that tomorrow. If this qubit is sort of uncontrolled, then that might be another reason to think of it as being like a heat bath. If you have pretty good control over this ancillary qubit that you're interacting with a system of interest, then it's one reason why we might want to prefer this definition. But again, there are lots of definitions. So in an example that you cook up, as long as you can justify your definition, then I think you have some reason to go with it.
I see. Thanks a lot. So this row should be taken as a heat bath, kind of something that we had. So it's not basically, I shouldn't, this row should be a bath. Is that what you're saying?
So the system of interest has an initial state rho. This is the thing on which we're doing work or from which we want to extract work. Then the battery is a different system. And since this definition is a definition of work, it doesn't directly define heats. We're actually not considering a heat bath here.
I see.
So thank you, Soham. Nicole, there's also a question on YouTube, if you have time. So,
Okay, maybe we could take
yeah.
one more question or so.
Okay, so there's one question on YouTube, which is that if row 1, 1 goes into row and then a linear combination of 0, 0s and 1, 1s, would there be an expenditure of work? So if it goes not only to sigma 0, 0, but to a mixture of 0, 0s and 1, 1, would that also mean an expenditure of work?
Yeah, that's an interesting question because it does violate our assumptions. And we made these assumptions for the sake of being able to justify a simple definition of work. The assumptions aren't always necessarily the most physically reasonable. So in that case, I think we'd have to think more about what is going on. Since there is probabilisticness in the final states, then we might want to regard that as resulting from a lack of control and an opportunity to think about heat.
Okay, cool, thank you.
And actually, since someone deferred his question about Maxwell's demon, maybe we could take that question, and then I'm afraid I'll have to go. But it's fantastic that there's so much participation and also that people are answering each other's questions in the chat.
Cool.
So can you bring Fernando back up?
Okay, Fernando, you're live.
I'm here. Are you listening
Great.
me?
Yes.
Yeah.
Oh, thank you. Thank
If you can turn on your video as well.
I cannot because I'm having problems with configuration of my computer.
No worries.
Linux questions. My question is about the Maxwell's demons, and I have a problem with this demon. I'm not Catholic, but I don't like it. And the reason is that, for me, since the demon has to perform work to open and close the door between the partitions, it should be a thermal machine. And a thermal machine needs two reservoirs at different temperatures. And thus, in my opinion, you cannot have a demon in equilibrium with your system. By another side, if you have a demon out of equilibrium with your system, you have flux of heat, and then you can not violate the second law. The entropy of one part of your system can decrease. So I'm wrong thinking about this.
Whether the demon exerts work to open or must exert work to open the trapdoor has definitely irked some people. So there's been a lot of conversation about it in the literature. It seems like you can construct a mechanism such that the door can open and close without performing work. There has been a lot of literature written about this. Probably the best references would be the review and the books that I mentioned, but also Charlie Bennett has written some very beautiful, simple explanations about Maxwell's demon. So I'll put one of them on the course webpage. And so I've looked through a fair number of reviews over the past few days. So I don't remember if it's exactly this one that talks about whether the demon performs work, but it might be in there, or at least this should probably have references about that question.
Okay.
Great. Thanks to everybody for all the participation. I'm afraid that I have to head out, but I will see you tomorrow.
Cool. Thank you so much, Nicole.
And yes, the lecture notes are going to be posted on the website.
Cool. Thank you, everyone, for the participation. Thank you so much, Nicole. See you all tomorrow.
Great. Thank you.
Okay, everyone. Thank you. Bye-bye.